The foundation of these large language models comes from a concept we call neural networks. Now, over the years, we have seen AI used for things like voice cloning, like the deepfake we're seeing all over the internet. It has been integrated into phone technology. We have used it in areas like uh, cryptocurrency. We have used it in even the chess game where we talk of the famous AlphaGo winning. We have seen AI almost every aspect of our life, from cybersecurity, facial recognitions, agriculture, handling and tackling things like climate change. We have seen AI actually doing lots of interesting things since it began to rise. But what is powering this AI? What is like the brain behind when you hear artificial intelligence? What is it all about? Because certainly, human being it's a fascinating species, but there is a part of human that we call the consciousness, and the consciousness, it we believe it resides in the brain of the human being. So when we talk about artificial intelligence, we said it is a technology or an approach where we make the computers to mimic human behavior. So that mimicking of human behavior, what is it that makes humans to be smart? What makes humans humans? Like I said, it is the consciousness. Now, but when you look at humans, when a human being is born, he or she does not know things except they're being taught in the process of time. The first people they learn from, or the first person they learn from, is usually their mothers, and then their fathers and other people around them. And then in time comes the parents will have to release them to the school authorities, where they also begin to learn from the school. And also with time, they form pairs where they begin to learn from friends, and then they continue to learn from other areas like movies and all that, and social networks. So that's how it is also with artificial intelligence. The machine itself is very dumb. It doesn't know anything. So in order for it to learn, it has to use an approach called machine learning. The machine learning, like we said, it's an ability of the machine to learn without being explicitly programmed. Remember, as a human being, we're not really having this strict way and said this is the rule, but the child sees what you're doing and the child learns as you're doing these things. So the child could see that, oh, mommy cleans the house, and with time the child too will say, I need to do the cleaning. Or the child sees you eating, and then the child say, oh, certainly I too could eat this thing. So the same way, the machine or the AI learn through this machine learning approach by looking at what we call training set, and then it makes prediction on the unseen data set, which we call testing set. So the machine learning has limitations. One of the limitations is that it has certain sort of rules or algorithms that it has to use to learn. So we said it is a rule-based system because of some of these algorithms that or framework that we have. So if it missed this particular pattern, it could get it either entirely wrong or it could get it very well. So there is this narrowing down that it could narrow down on a particular task, but it can't really do other tasks so much. So, and that brings us to the whole concept of AGI, which we have not gotten to, because the AI could be very good in a particular task that you train it, but any other task you don't train it, it's very, very poor at doing that. But when you see the human being, it doesn't work that way. The human being may not have been good in a particular thing, but they don't really feel entirely. They'll still be able to do that. So we have seen this machine learning applied in different areas like spam and non-spam in the email, and also showing you guys in the medical field where we use them for classification and also for prediction purposes. However, we wanted to go deeper to mimic the true intelligence that comes from humans. So that gives rise to a very interesting topic called neural networks. And inside that neural networks, which is a subset of the machine learning, comes the deep learning. So if you could see uh, sorry. Yeah, I could. Okay, before I comes to this one because I have so much material, so let me try to prioritize them. So we have the deep learning. So the deep learning, what it does is it extracts patterns from the data using the neural networks. So let's see what this deep learning is, and then I could tell you guys more about why it was necessary. Let me see. So I think we could start from the beginning. So, like I said, what we are just going to be looking at it's okay, sorry. Okay, great. I don't know if you could see my slide. You can see my slide, right? Can somebody mute to confirm?
Yes, yes, yes.
Okay, good. So, like I said, the artificial intelligence is the big or the universal set or the model set, like we said in mathematics. But what powers the artificial intelligence is the machine learning. Then, underneath the machine learning, there is another subset we call the neural networks. But the neural networks is what powers the deep learning. So, what inspired this whole thing or this technology was looking at the human brain. When you look at the human brain in sort of a detail, you will see what we call the dendrites. Now, the dendrites send this sort of what we call synapse, like a shock to the next dendrite. So when you look at the connections in the human brain and even looking at the neurons or the neural system, you will see how these connections happen from the brain down to the spinal cord, and each of them follows down to the nerves that we have in our cells. So there is that dendrites, which are the connections that send these shock waves to the next dendrite, and then we have the nucleus and we have the soma. Then there is the axion, and then there are so many other things. But the most important thing is I want you to always look at it, that dendrite that sends that shocking wave to the next cell. So based on this kind of architecture, the scientists begin to think, can we create these interconnected systems just like we have the neurons in the human brain, which in this case we can call them the nodes, organized in a layer to process data from one input layer to the other till we have an output. So remember in earlier versions, I told you guys about the classification tags, the regression tags, and so on. So it is in that line that we building this, we're looking at how the brain is organized to build this. So that when a particular reflex action is triggered, this dendrite will send or they will power or they will fire to the next dendrite that will pick it. So, for example, when you put your hand inside the fire, while you instantly removed the hand, is because the brain has sent a signal that this thing burns, and immediately you see that particular neuron that is responsible for withdrawing the hand will trigger, and immediately when it triggers, you would take away your hand from the fire. And most times these things happen instantaneously, in such a very fast way that you don't even know when you withdrew your hands. So that connections, that sort of moving from the input down to the output where these triggers happen, you will see that the same way we build that for the neural network architecture, we have an input layer which we put in that data. Remember, in the case of putting your hand in that fire and withdrawing your hand in that fire, the input there is that it sends to the fire that we have is now the withdrawing of the hand is the output. Then the input is that decision that you're making if the fire going to burn or is not going to burn you. So stuff like that. So we have the hidden layer which we don't see, and then we have the output layer which is the actions that we take, to withdraw our hands from the fire so we don't get burned. So the component of the neural networks is made up of the neurons, like I said, just like in the human brain, we have, or in the neural system of humans, we have the dendrites and other connections, and then we have the layers. So just like we have the myelinated axion, the same way we have in the computers is going to be the hidden layer, and then we have this whole layers that has to be, which is the first layer is the input, the hidden layer, and then the output layer. However, we also have this node that you could see here, and those ones take in what we call the weight. So that information that you have to store in this node, just like in the human composition, the DNA store the whole information of that particular person. Like for example, when you looked at the Egyptians' mummy that they take from the pyramids and other tombs, they when they want to check that particular human, they can perform some sort of DNA on those bones. So they could scrape part of the bones, and then from there they could go and check. And you will see most of the time the information is stored about that particular person. So they could use that information to now begin to look at these ancient people and how they were made up from, and all that. They could even be able to detect what caused the death of that person by just looking at the DNA of that person. So the DNA retain the information. We see that a lot in issues like paternity, where maybe there is a dispute on the paternity of a child, the parents will say, okay, let's do a DNA. So because the DNA have that information, so if you are the father of that child, there is that 99.9% that the DNA of that child will resemble that of yours because it has that information that was stored in your cell that was transferred to that of the child. And this is why even in the Christendom, you see people talking about ancestral curses, ancestral limitations, and all that. I saw a study that was trying to look at if curses are transferable from one generation to the other. Quite an interesting study, that they were trying to establish. But that's because this information are retainable from one generation to the other. So that information that is contained in that DNA, in the case of the computer, these are weights, these are in form of weight and all that. And sometimes one node can hold more information compared to another node. So that makes the whole thing to be much more than that. Then we also have the activation functions that ranges from the sigmoid, ReLU, and also the times. function. But I'm going to talk about that in a minute. So let me quickly move back to the PDF where I could tell you by. So why this deep learning in the first place? Uh, okay. Okay, let me not go to this slide. Let me still establish some concepts before I come back to that in a minute. So permit me to still go back. So let's look at what the structure of the neural network looks like. So remember that just like the human brain, we have the input layers, the hidden layers, and the output layer. And this hidden in the human brain, we talked about the synapse that comes from the dendrite. So that dendrites are like connection. Even though in the human brain we don't really see that physical connection between these dendrites, but most times it sends this information in form of like a shock wave, and then it moves to the next dendrite. It picks it and also sends it to the next one. So, but in a computer neural network architecture, we have these connections that connect the input layers to the hidden layers and down to the output layers. So this whole line here that you see, these are the connections that actually carries this information. And then once you move from one hidden layer to the other, you also have to have this connection until you get to the output layer. So each neuron computes a weight sum of the input, applies an activation function, and passes it to the resulting layer. So it means that in each of this hidden layer here, there is going to be an activation function, which is going to tell the information is processing either to multiply, to add, or to divide. So that's basically that sort of transformation that will happen. And then once that is done, it passes it to this next layer. And once that is also done, it passes it down to the output layer. So the input layer receives the raw data, which can be in form of pixels, it can be in form of values of an image, and so on and so forth. It can even be in form of text. It can even be in when we talk about the image, things like CT scan, X-rays, even pictures, and all that, we could feed it to the system and then it will be able to process them. Then we have the hidden layer, which process this data by using the activation functions to either sum, multiply, or divide. And once that is done, it passes it to the next layer, which is called the out. It continues to pass it from one hidden layer to the other until it gets to the output layer, which produce the final prediction or classification task that you give the AI to do for you. Having said that, let's take a look at a more deeper thing that I want to say. Why deep learning? But we'll come back to this example in detail. But when you look at this example here, this is a picture that was fed to the deep neural network. So what it's going to do is that it will break it down. So at the low, it will start from a lower level of trying to recognize or extract pattern. Then it moves to the mid level and then to the high level. It continues to do that until it processes it. So when you feed it the picture, it will split that whole picture into several pixels. So let's say one of the pixels will look at the nose, another one will look at the mouth, another one will look at the shape of the head, the face, and all. So many, it will break it into lines and edges. That's a low level feature extraction. So once it has extracted, remember we talked about the activation function in this hidden layer. So once it has processed here, it moves it to another layer, which you can say, for example, a mid-level. So once it moves to that layer, that one will assemble what it has learned from the lower level. So maybe it assembled it into eyes, into nose, into ears, into so many things. So once it has assembled it into that, it will begin to move sort of like the window frame and continue to be putting them together until when you move to the high level, it's kind of compact then. So you will begin to see this max pooling and all that as we continue to move forward. We'll talk about some of this concept. So there is going to now be that high level that will now put these things together that it have learned from all these hidden layers level. And then at the end of the day, it could output them for you. So that's how most of these systems like computer visions work. So I keep going back to me. Sorry. So that's how most of these layers work. So let's look at a typical example of some of the application of this neural networks. We use it a lot.
Can I quickly have a couple? What exactly happened in the hidden layer?
So the hidden layer actually processes the information that it receives from the input layer, and it processes the information by applying sort of transformation. So what that activation function could do, the activation function could help in, for example, adding the weights together. It could also act as multiplying the weights together. It could divide, depend on the task in which we're actually looking at hand. So when we go further, I would emphasize more on each of these, and we could see how these activation functions look like. So the hidden layer is just the information processing box. So just like when we send a shock wave from one dendrite to the other, that dendrite will process that information to tell that child to either withdraw their hands from the fire or to allow the hands to burn. So that's that whole transfer of information from one layer to the other until the decision is finally taken is what happens in the hidden layer. So does that answer your question?
Yeah.
Okay, but when we come, we will still look at some of this in detail. So we have the image recognition as a very famous example of where the neural networks works. It helps us to identify objects in photos. Like I showed you, when you feed the neural network a complete picture, you see it breaks them into several pixels. And when it breaks them into several pixels, it will now process them and assemble them. And I could tell you this example in real life. I remember growing up, I started learning artwork because I liked sketching. I do sketch. So my brother now saw my sketch and then he said, "Oh, to perfect your hand, it will make sense if you go to someone that is already an artist that have a shop, and if you grow up in the 90s, you will certainly know that, the handwork was quite famous in Nigeria. Many children were put in to learn one skill or the other because most times parents feel they were whiling away lots of time playing. And trust me, then I could play all day, especially football and also some war games and all that. So we could create all different play in different seasons. So I felt bad then because I have to wake up early in the morning to go to the workshop to go and learn the artwork. But then I enjoyed it because I love sketching. So I easily just fit in. So the first thing I remember then, I started learning different things from woodwork, art that has to do with creating or producing cards, for Valentine and other special occasions. And then later on, we moved from carved woodworks and all that. We now moved into pencil work where we have to sketch human pictures. So the first thing I remember then, the example that the guy taught me I can't really call him. I think then we call them Oga or something. Yeah, Oga. So the guy, which is my Oga, the first thing he taught me then, what the next thing he taught me on how to sketch a human. So what he does was he used a ruler to, divide this picture into, this straight line. So let's say you have a picture of, let's say, 2 by, I can't know how many centimeters now, but let's say we have that picture. He divides it into like let's say 50, no, let's say 10, in 10 places first. Then he further split that 10 into another two. Then he splits it again. So it's splitting several pixels. Then he will rule them. So it's more like he put it back into like a grid. So he will now use the ruler. So he puts the ruler. So then he comes to the cardboard paper that he's using. He also drew that the same lines. So by the time he drew that same line on the cardboard and also on the picture, he will now begin to use the pencil to sketch. So when he comes to the eye of the picture, he puts the ruler on that. So when he puts the ruler, he will just focus on that, and then he will draw that side. So he moved to another pixel, another a square, he will draw the same. He moves to another square, he drew the same. He will keep doing it until he drew everything that is in the picture. He will put it. Then once he finished, the next thing he will now begin to use the pencil to clean that lines that he has put on the cardboard paper. So by the time he finishes, you will see a whole image of that picture has been replicated on the cardboard paper. But now it's just going to, the only difference will be it is now in pencil. So the same way, the neural network works. It takes that picture, splits it into several pixels, and then it processes them and assembles them again. So if you want to differentiate between a cat and a dog, you have to feed the neural network algorithm, let's say a convolutional neural network in this case, you have to feed it with several pictures of a cat and several pictures of a dog. Then it's going to now look at each of these features. So it will break down each of these features. It will look at what makes the cat unique and what makes it different from the dog. If you want it to predict cancer from non-cancer, you have to feed it with the image of the tumor. So it sees what that tumor looks like and then how the healthy images looks like. Then it classifies it. So instead of the radiologist to come and do it, imagine if you go to a hospital where there are thousands of these images for the radiologist to come and do the classification looking at these images. So what we just need to do is to help that radiologist to reduce his or her work by training a machine learning algorithm that could do that for us. So for us to do that training, we will need the expert to label what is a healthy patient and who is a patient that is sick. Then when we feed the machine learning during the training, then when we now have new images, we don't need to go back training. We just show the machine learning algorithm and tells it, check, what is this? Is it a healthy patient or a sick patient? Then it just looks at it and says, oh, it's a healthy patient. So the same thing, if you are doing it for a cat and a dog, you feed it with what's a cat and what's a dog. Then in the future, when you show it an image and say, what is this? It will tell you this is a cat or this is a dog. So we use it for this object and image recognitions. We also use it in natural language processing, like sentimental analysis. We use it for also text and all that. And that's where I told you guys that this is where the chat GPT evolved. The chatbots that you use, all these things came from a particular aspect of the neural networks that we call recurrent neural networks. So it's from all these recurrent neural networks that we're able to design this. So it will split all these text into several sort of context. Like it breaks them into little things that we now looked at them, and then we removed unnecessary things like quotation mark. Is it cap? We turn it to small letters, and then we will now be able to create this future sort of matrix for each of these texts. And then we will now be using the weight, and then it will tell us what the next text should be. But when it comes to natural language processing, I could talk about some of these things. Then we also use it in speech recognition. A good example is the Alexa that you have. You could tell the Alexa, I want you to play me this music. It plays. You could tell it to turn the light on in the house. It does that. So stuff like that. It could be able to recognize your voice. So all these things also is the neural networks that help us in doing that. Then we also have interesting aspects like robotics. So in areas like supply chains, robotics are created, to help, facilitate or reduce some of these things. Especially when you go to the industries, there are some heavy lifting jobs that human being cannot. So we train the robots to be able to do that for us. And you could see them doing those things. And right now, with the whole ChatGPT sort of large language revolution, in fact, the robotics are becoming more humanoid compared to how it was some years back. Then we also talk about the areas like image recognition, which I emphasize, the speech recognition, the natural language processing. Then there is the autonomous vehicle that we see people like Elon Musk are doing a lot of in that area, where you have the Tesla sort of cars. All these things using computer vision to be able to do that and run these things effectively. Then we also talk about in the banking sector, it will help us in fraud detection. Most times I told you guys about cybersecurity last time. We made mention of how AI is helping out in that area. So we see how it does a lot of interesting things there. Then in the medical side, we use it for medical diagnosis. Like I said, we want to look at an image from from X-ray or CT scan. You will be able to help you to see if this thing is true or this thing is not the other way around. So it could help us in diagnosing cancer down to even, if a patient required a brain surgery. The brain surgery is very complex and complicated. Most times, it's not everybody you have to open their skull. And so sometimes when you want to check if there is a stain in the white matter of the brain, because if there is a blood, maybe an accident happens and the patient hits their head and maybe they entered into coma and all that. Most times the neurologist will have to check the I think MRI scan of those patients to see if there are blood stains in the brain of that patient. So if there are much blood stain that cannot easily dry up, they need to open the skull to drain that blood from the skull, so it doesn't mixed up with the brain matter, sorry. So what they need, so if you now, most patients don't survive after that surgery. Most of them died. And I'm saying some of these things really based on first-hand experience. When my sister had an accident, then I had to be in the hospital. I think that was during my 300 level. Most of the patients that they operated from that surgery, most of them didn't survive. Luckily for my sister, they didn't have to do that because the blood stain was very minimal. So they said it's going to dry up, and it did dry up. So, but other people that were, it was a very complex case that they ended up have to do surgery for them. Most of them passed on. There was a man that was not quite far from where my sister's bed was, and I remember he was quite jovial and very, very, friendly. But after the surgery, some weeks back, we came back. When I came and asked, I learned that he passed away. So that kind of thing, if you have AI in that area, it could help the neurologists to minimize this kind of loss, so they don't have to open everybody's skull. What they just need to do is to train this um, neural networks or deep neural networks that will be able to recognize a healthy brain and a brain that has blood stain, or a brain that has a minimal blood stain and the one that has much blood stain that will require a surgery. So if that brain doesn't require the surgery, it will classify it as negative. If it requires a surgery, it classifies it as positive instance. So that way, they don't have to keep opening everybody's brain at this, without and all that, and they can cut off that death mortality cases that happens after the surgery. So it's very, very helpful in that area, like medical diagnosis. Then we have in the human resource management as well. It will also help us to do a lot. How about energy management? Like we know these days the world needs a lot of energy thing. Like a good example I could tell you is the computing the data centers that we have. Most of the data centers, remember last time I told you guys how much energy we need for a chat GPT 3. I told you guys it emits a lot of carbon dioxide and also the greenhouse gases. So we need a system to manage this energy such that we will not have a lot of, because if there is so much heat in the data centers, it's likely going to go on flames, and that will cause a disruption in some of these models for people that are using them. So they have to find a way to cool the system by, putting this water recycled at all times to make sure they keep it cool. Because every token that you process, or every sentence you write, the computer, the model will break it down into several tokens. Now, imagine giving a chat GPT a full one page. You know how many tokens that is. So each of these tokens, when it breaks it down, it will save them as weight. And at the end of the day, it will give you back feedback. So this whole process that go in that chat GPT whole thing, it has to use a lot of computational resource. And if you don't have a way to manage this resource, it will definitely have effects on it. That, just imagine on your computer now, if you have a lot of data and you are training some of this model, it could take you weeks, months to process them because it's quite large. So this whole management between these resources, you have to make sure you keep it in a cool environment so it doesn't get so much hot and all that. You can also be able to build recommendation systems from this network. And also we have the financial forecasting. These days, there is a lot of volatility in the real world, the cryptocurrency and all these other stock market. So you need this kind of systems to be able to forecast, especially things like the long-term short memory, LSTM, help us to be able to make forecasts about what's going to happen, and then you could be able to take action. In agriculture, of course, you can use it for pests. I remember during my PhD, one of the one of the exercise that was given to us was to develop a sort of our own system in areas that we want to apply these deep neural networks or whatsoever. But I think in that case, during my PhD, it was on computer vision. We were looking at computer vision. So we were to apply it in computer vision. So one of the area that I did that period of time was on insect. I think it has to do with wheel screen splash from insects, because like during the summer there is a lot of insects that you see during the summer. So when you are moving with your when you are driving, most of the time your wheel screen are likely going to be impacted by these flying insect like birds and beetles and all that. It could come and hit them. And most times, because you're traveling at a higher speed, the velocity of your car and that of the flying insect, immediately it hits the screen, it's splashed. And when this whole thing splashes a lot, most of the time it can slow down your wheels. It could cause disruption in your driving. Even in things like airlines, some of the crashes is caused when a lot of bed entered into the engine and all that, and so if you have this monitoring system that can detect these things before they impact and is going to find a way to avert them or is going to find a way to take care of them before the impact, it could make sense. You can imagine if we have a system that, or some sort of like a camera that is going to look at if these birds are coming, and it could alert the pilot, and then the pilot could find a way to maneuver so he doesn't have to have a direct correlation with the birds. It's going to save a lot of lives and it will minimize crash. So stuff like that, you can also use it in agriculture to spot pests. You can use it to detect if there are some crops that could easily attract some sort of pests like beetles. You can spot which beetles are dangerous and which ones are agents of pollination. And then the ones that are dangerous, the farmers can find a way to take them out from their crops, and then it doesn't have to affect them. And then the ones that are agents of pollinations, you could allow them to thrive. So stuff like that, you could use them in agriculture and even in climate change to be able to monitor weather and forecast if there's going to be rain and all that. Then how about customer service automation? Most times you chat with chatbots. Most times you tell organizations, maybe you logged into a website, you see someone will come up and say, how can I help you? And then you can start chatting with that person. So what does that is a chatbot powered by these neural networks that does some of these things. Then we have in personalized medicine, especially when we talk about multiomics, when we have to look at genomic data set, proteomic data set, clinical data set can also be integrated, and also when you have other omics data set that we could bring in from the clinic. When you combine these things, you can be able to have an effective overview of someone, and then how you could be able to manage that person's health. For example, you could be able to recommend drugs that that person could be on. And then we have biometric authentication. Of course, you are very familiar if you do the visa processes where you go to thumbprint and you put your fingerprint and all that during biometric. That biometric stuff you're doing uses that computer vision coming from neural networks. Like I talk about the game which we have, like the chess game, like even in art and music, we began to see musics that were generated by ChatGPT, and I think I could look for the music that I generated recently using ChatGPT, because most of the time when I'm praying, sometimes I get some inspirations and then I sing some songs and I record them. So what I did was I put that song and tell it and say, okay, this is I want this song, to, and it puts everything, garnish it, put the sound and everything the way I want it. So probably I could send it to in the group or something, and you guys could listen to the song. It was AI that I used to generate that song with. So we are doing so much things, we can be able to do these days with AI. So the next thing I want us to look at is how does this neural network, how does it learn? How does it work? Because it doesn't make sense if you don't understand how this thing works. You see, the neural network learned from what we call the forward propagation, and also the backward or back propagation, but which we will look at each of them in detail. Now, remember, when we are talking about the forward propagation, it's just like a feed forward, meaning it passes that information from one layer to the other. So, but when we are talking about the backward propagation, we are just talking about regurgitating it. So it means instead of moving forward, it must have moved forward and have learned something, then it has to correct that something by going backward. So that going backward will be much like a gradient descent approach, and then it will going to now begin to. But if we are saying this thing have to learn something, then it means that there is going to be a room for error. Remember, in the case of the child, when that child is learning, if you have a little one, you will see that if the child does something that is wrong, you spank the child and say, "Don't do this, it's wrong." And when the child does something right, say, "Oh, well done, you do this, you're doing well." So that feedback approach helps the child to be able to, in time, minimize loss. It means the child begins to say, "This one is not right. This one is right." Like my older daughter now, she could tell the little one and say, "Don't do this. Stop. It's not right." Stuff like that, because now she knew, because when she does what you tell her and say, "No, don't do this, you do this." So that whole feedback approach, where the child learn the same way the network learn. So, but in this case, when you input it, it takes it one of the input and pass it to the next node. So, and it passes it via the connection, but that connection will carry weight, and this weight may not be the same, but I'll emphasize as we move forward. So maybe from the first input layer to the second input layer, probably you have just two. It requires just two, and then the next weight is 6, and then the next one is 36. The next one can be 64, and all that depend on how you stack the layer. So that forward pass is that transmission or translation of the information from one layer to the other, until you get to the output, or and then again, like I said, you will have to look at the errors, because it's not always that these things are right. So the first time you may see the error is very large. The second time it may not. So what the neural network works is that it works with a very critical thing we call these batches. So because of the batches, you can have up to 10, 20 batches, depending on how you want to split the data. So when it trained the first batch, you will see the learning error is quite high. But when you go back the second time, you will see it will reduce. When you go back the third time, it reduces until, as you keep going back, keep going back, you will see that it reduces, very well. So the flow of the data through the network in a feed forward approach is what we call the forward propagation. However, when we are now reversing, when we are coming backward through the back propagation approach, we will come looking like, it will look like a gradient descent, because you are now, like, you have climbed the hill, you are now accelerating. So most times when you are coming down from a hill, you will likely want to maximize it by following the shortest route. You wouldn't want to use that long route that will take you a long time. You want to say, "Okay, let me use the shortest path," and all that. And we could talk about that. And when you are familiar with calculus, you will know that there is a very good way is a very good place where the chain rule helps us, because the chain rule will now begin to help us to be able to observe these local minimals, and these local minimals helps us such that we don't get trapped. And I could go on, and like I said, I always want to keep the mathematics out of these things. Then we know the updating of the weight happens because we have gotten a feedback. So if we get some feedback from the first iteration, it will now adjust the weight. Then if we go back again, it adjusts the weight. So that cycle of going back, and forth helps the network to be able to get the optimal weight that it could be able to, perform better. So, however, it doesn't just rely on these nodes and connections. There is, remember I said inside the node, inside, the input, the input layer, the hidden layer, each of these nodes, there is what we call the activation functions that process the information. So the activation function are non-linear sort of functions that are embedded in the nodes or the neural networks, enabling them to model complex patterns. They determine whether a neuron should fire and how strongly should it fire. So like the synapse in the human brain, which fires or trigger to send message to the next I think there is those message neuron in the human brain. We have the message neuron and we have the receiver neuron, something I can't remember the neural networks again, from biology, but I know there is a message messenger or something, and then there is the receiver and all that. I can't remember, but if you can go back to reflex action, you can see how these things move. Like, don't forgive me because I've left biology a bit a long time, although I'm still in the medical field, but I'm not concentrating on those things again. So if the transfer of information happens in a spontaneous approach, but now that synapse that fires is because it is the synapse that is responsible. For example, the child puts his or her hand inside fire. You don't expect the synapse, the neuron that is responsible for the leg to react. It is the hand that is burning. So it is the neuron that is in the hand that will fire to tell the child to withdraw the hand. So the one in the leg, of course, it will fire because the whole body is going to check backward to move. But the one that is responsible directly in carrying out that action is likely going to be the hand. So the activation function is the one that processes this complex information that is coming from the next neuron. So when this next neuron takes this information, it's going to carry that data, that raw data, and attach with the weight and passed it into the neuron that has the activation function inside it. For example, this activation function here is for summation. So it will tell it that it should sum x1w1, x2w2, down to xnwn. It should sum them. Once it sums them, it will remember that the summing is not going to be always correct. There would be that presence of bias or something, if you remember minimization and all that, maximization. So that summing, once it summed them, it will pass them again to that activation function until it gets to the last output layer that will also pass it on. So because this whole thing happened in a convolutional manner, so there will be a lot of pooling, there will be a lot of summing, and so many other things will happen. So before the output layer, you will definitely have another activation function that will now open it. So it's more like embedding. So when we put it, it will now get to a point where it will open it again, and then it gives us the result. So like I said, if you give it the picture of a cat, it's going to break down each of the things that are in that picture into pixels, and then it will play around with them, look out for the patterns, and process it until it gets to the last point where it will now output for you and say, this is a cat, and all that. So the activation functions is very critical in helping us to be able to manage these complex transformations that happen inside the neurons or the nodes. Sorry. So The activation function has several types, okay? Because there are cases where I don't need to use a very complex activation function. There are cases where I just need to use something very simple and all that. So the sigmoid function, for example, it's very, very direct, where I could be able to know what is happening. It's just bent. Most times, if we're using a linear sort of problem, the sigmoid function comes into play, and it's very, very effective. And I think it moves from -1 to 1, the range. Then we have other functions like the tan function, where we know it could move, down to, I think, from -1 also down to 1. But you could clearly see this is applicable to nonlinear relationships. We have the ReLU as well, which also moves from a positive function like 0 down to the number. And then we have other one like max out, ILU, leaky ReLU, and so on and so forth. We have so many activation functions. However, let's look at them in detail. The sigmoid function is very good in binary classification problems. However, the limitation of this function is that it suffers from vanishing gradients. So most of the time when the complexity increases, you can't manage it again. I remember I told you guys last time that the linear functions has this advantage of interpretability, but the more these data become very complex, the linear function can't be able to manage them. So one of the issues it suffers is that vanishing of the gradient, but it's very, very nice when you are using binary classification problems, because the range comes from 0 to 1. Like you could actually see how it moves. So I think this one couldn't be a good representation. Anyway, we have come from that 0 to 1. And then when we are talking about the ReLU, which is ratified linear unit, so the ReLU was more like building on top of the sigmoid to correct what the sigmoid couldn't really achieve. So the ReLU works better in the hidden layers. So remember the input layer, the hidden layers, the output layer. So it works better when we are operating in the hidden layer. It's very fast in convergence. However, it's managed to avoid vanishing the gradient descent. So that vanishing that this sigmoids could not handle, this one was able to avoid it. And it ranges from a close 0 range. Oh, okay, I see why this is open. This is an open function, so it's fine. So this is work from a closed 0 range down to infinity. So it covers quite a wide areas in all that, and you could actually see one of the reasons why it converges faster. Then the tan activation function, it centered the output better for some optimization tasks. And I think especially when you have a nonlinear relationship, I think the tan actually does a very good job there. And then the softmax, when we have multi-class problems, it works very well in it. Just like the sigmoid, it also covers the range of 0 to 1 in the output layer. So now let me see if I could switch. Okay, yeah, let me see. Later on, I could switch to the other material. So what is deep learning? So then remember, we said the neural networks has the input layer, the hidden layer, the output layer. Now, when we begin to stack so many hidden layers inside the neural networks, it's no longer a shallow network. It becomes a deep network. Usually, I think networks that are above 3, I think they are considered deep learning. So when you have this first 1, 2, and 3, most times we say it is a shallow network, not that deep. And most of that time, you can be able to use your normal PC to train them. But the moment you begin to go very deeper, you will see that your normal PC wouldn't be able to handle it. So that's moving away from stacking, this is a hidden layer. In the neural network, we have just one of it. But in the deep neural network, we start adding the layer 1, 2, 3, 4. We keep adding. And the more we add, the more complex it becomes. However, the advantage we have is that it's much more precise or accurate most of the time when you have it. But computational resource, it will demand a lot of computations. Remember, each node will have to have an activation function that performs will have some functions that perform some sort of computations, pass it to the next node, pass it to the next node. So you could imagine how long it will take if you have so many of these layers stacked. And remember, the weights are not going to be the same. If this weight here is 6, the next weight is 36, for example, the next weight here probably you say 64, the next weight here maybe 120. As you increase the weight, yes, it will prioritize it, but it will take a lot of computational resource to process. So the why deep? Because it captures hierarchical features such as the edges, the shapes, and the objects in images. Because each of the layer now will specifically focus on one thing. So maybe this layer will be responsible in looking at every pixels that are in that picture. The next layer is going to now begin to assemble these pixels. The next layer is going to now look at each window frame, what is happening. So it could look at the nose and say this cat has its face this way. The dog has its own snout this way. Stuff like that. It will be looking at all those things. And then at the end of the day, it will say this is a dog and this is a cat, or this is cancerous and this is not. So stuff like that. So as you start the layer, it becomes more narrowed down to attack to be able to do one specific thing and then put everything together. So example of these deep neural networks, we have this convolutional neural network, which we call CNN. We handle image classification. Anything that has to do with image classification, we have the CNN does very well. Although it could have several architecture, it may not be one architecture. We could play around with it. But when we come to text generation, the recurrent neural networks or RNNs does this very well. And also the transformer architectures that we see that give birth to ChatGPTs and the rest. Then there is also these recommendation systems or engines that does all these other things for us as well. Now, the popular neural network architectures we have, remember I briefly mentioned about the feed-forward neural networks, which is RNNs. Then we talk about the convolutional neural networks, which I said mainly this works for images. And then the recurrent neural networks, which work for sequential data set, and also text, like we say, generally handle text, and all that. Then we have the transformers and the breadth. So those ones are what gave birth to the large language models that we are talking about. So the convolutional neural network architecture usually looks something like this, where we have the pooling or the convolutional layers, which are generally the hidden layers. So these ones will be the ones that will pieces those images into pixels, will combine them and transform them and all that. And at the end of the day, it will open it up to the last layer, which is fully connected layer, and then it passes to the output layer. So we have each of so you could see how the architecture of the convolutional neural networks usually look. Then we also have the recurrent neural networks, how the architecture of this network looks. We have the hidden layer also, and we also have the input layer. However, you will get to see that we don't have the pooling or the convolutional layers in the recurrent neural networks. We just have the input layers and the hidden layers, then we have the output layers. However, we have what is very interesting, we call it memory cell. So that memory cell is the one that retains some of these tokens and be able to process it. For example, if you tell ChatGPT to tell you a story of the tortoise, because maybe the ChatGPT must have been trained on several stories or African stories, folklores of tortoise, it will be able to give you or regurgitate a new good story of tortoise for you. So that fact that it could be able to retain those information is because of what we call the memory cell. But in the convolutional neural network, it's not the memory cells we have, rather we have the pooling or the convolutional cells. Why do I keep calling them neurons? Node. So it does those things for you. Maybe because of the brain stuff. That's why I keep calling it neurons. Anyway, so sorry, before I proceed, do you have any question?
Right.
Okay. Okay, so go on.
I said not yet.
Okay, so we are fine. Okay, so let's continue then. So, the next thing we have is we need to understand the concept of this forward propagation that we emphasized earlier on. Now, in the forward propagation, it is that process of passing the input data through the networks to produce an output. So remember, I said that forward feeding of that information from one network node to the other is simply that what we talk about the forward propagation. So it is made up of the input data which is fed into the input layer or the hidden layer that will pass it to the next one. And then we have each layer computes the weight sum and apply the activation function. So then we have the output layer which produce predictions or it could be probabilities, it could be the labels, and so on and so forth. Now, when you looked at the input layer here, usually the data that is coming, let's say this is the input layer and all that. This is just a simplified version, okay? So when you look at that inputs that are coming, this is, for example, we have the one that represents the constant, and then we have x1, x2 down to xm. Now, each of them will carry a weight. Let's say the constants, we assign a weight called W0. The next independent features, we call it W1, and so on, till the last one, we call it Wn. Now, the moment we feed this to the input node, it's going to do computation because this is called summation. So it will do some summation here, and then it will pass that what it has processed to the next layer here. So to the next node. So that part where it's passing this information to the next node is in such a forward manner. And then once it passes it to this to the next node, that one too will continue to pass it until that layer layer that is close to the output. Now it will now look at it. So suppose we have several millions or thousands of this particular thing replicated. You will see that if this weight is greater than the next weight we are going to have, or is greater than all the weights in this layer, then this one will fire. So it's not going to tell us this is a dog, or it's going to tell us this is a cat. Why? Because the prediction probability was quite higher, and that's why it was able to trigger and say that's what it suspects it to be. So if we want to express it mathematically, it is just a sort of a linear combination that happens inside here. So when you have the prediction or the y cap is going to be equal to this g. This g is a nonlinear transformation that happened. But what is this nonlinear transformation, this summation here that you see? This summation here is nothing but just a linear combination of all these weights or inputs here. Remember, we have this W, which is W0 plus the other ones, which are these subs here. So it's going to be X1, W1, X2, W2, down to plus, dot, plus, no, dot, plus XMWM. So that's why we have summing from n to I equal to 1. But if you don't want that, you could say you are summing from n, then I equal to 0. So when you do that, it means when it's adding, this will be W0. So it will be X, I will only have to start from 1. And remember we said this I is the constant or the bias that we introduce, as a result of a random error that could happen. So that's why we have this. So this, what is happening inside the node is nothing but a linear combination of the weight and also the features that you are putting inside the input layer of the model. Then, in the case of the backpropagation or backpropagation of errors updates the weight to minimize the loss function. So like I tell you, at each batch, because we are likely going to feed the data to the algorithm in batches. Now, at each batch that you feed the data into it, you are likely going to see that the learning rate at the first time you feed it, because most times this deep neural network, when it's running, you will see the graphical display of the learning rate. You are likely going to see that at the first run, you will see the learning rate is much. But the moment you go again the second time, you will see it has learned something, then it will readjust them. So that readjusting that you are doing in a backward spin that you keep going back to learn, you go back again, you go back the second time, is what we call the back propagation. So the backward propagation of these errors is simply we are updating the weight. So the initial assignment of the weights will not be the same when we are going back the second time, because you must have seen the model must have seen the algorithm must have seen that what is taught in the initial time is not true. It haven't learned everything completely from that picture you give it. So if you go back again, it will learn another new thing. If you keep going back, it keep learning until it gets to that minimal time point where the error is very small. So when you look at the architecture here, you have this gradient of the errors. So it means you are like coming back, and all that. And we'll see that I think in the next page. Yeah. Okay, before I come to the loss function. So you will see that each time that you are coming back is more like you are descending. So as you're coming back, it's not more, you are descending because you go from 3, 2, 1. You learn something, you are going to come back again to go from 3, 2, 1. You come back again, you go from 3 to 1. So at each time you go, you are going to subtract the error minus the difference between the predicted and the output and the actual outputs that you have. Remember, if we are doing training, we have the true level during the training. You have the true level. It's only the testing that you usually withhold the true level from the algorithm, and then you tell it to predict, then you compare to see if what it predicts is actually getting it right with what you have as a true level. So you will be able to subtract what it learned from the first time it goes from the actual difference to see. So if at the first instant, the actual thing, if it is a cat, it's supposed to be a particular percentage. And then when it predicts it with maybe 50%. So remember, if it's a cat, the probability is supposed to be 100, right? So at the first move, it learned that it predicted if it's a cat or a dog, it gives each of them 50%, 50%. Then when it comes back the second time, it learned something and increased the chances of a cat to 60% and the chances of a dog reduces to 40%. So when you subtract that 60 from 1 from 60, it has an error loss of 40, which is still much. It go back again and update. When it updates, probably it predicts it gets it with 75%. By the time you subtract 100 from 75, you discover that, okay, we have lost just 25%. You moved again until maybe you get to a point where you are having 99. So at that point, you see the error is very small. And that means it has learned almost everything from the training. And then it could be able to move. So we have the outputs, the predicted outputs. And remember the same architecture, the hidden layer, the input layer, the hidden layer, and output layer. And then each of these layers, of course, remember we said it will process the weight and also the X. So once it moves, it will pass it on to this one, which will be, let's say, W1, W2, W3. And then if it is a dog or a cat or something, this fires. And then he said, this is a dog and this is not. So stuffs like that, at each of the layer. So this whole process of iterating and coming and doing, like I said, it's more of a gradient descent. And if you look at a 3D image of the gradient descent, you are always going to be looking at what is the shortest path that you are going to get to your do I call it a local optimum? Now, you will have to explore each of these to see where this whole thing will be much easier for you. So by the time you look at the shortest route, you will always want to take that shortest route. However, you have to also be careful because you can also get stuck in a local minima. So you have to be looking at it and say, okay, what is it that when I come and all that, and these local minimals and all that increases, as we begin to look at very complex data, these things could increase. So that updating of weight, where we have to keep coming, from the output, we update to correct them. We go back again with updates. We go back again with updates. So if you have this X1, X2 down to Xn, W1, W2 down to Wn from the input layer, you carry out all these transformation here. Remember, we said this is just the linear combination. When you perform all these linear combination, the next thing you have to pass it out to the activation function. So the activation function will do the transformation, which will now give you an output. The output will now say it is let's say, probability of a certain class of that particular input that you give it, or it will be a prediction probability or a label. So if you are looking at a prediction probability, probably let's say you get a 0.9 or something. That means, let's say that 0.9 is a dog, and then that is not the other way around. Now, each error that you have, if you know calculus, it's just like when you differentiate the first time, you differentiate the second time, you differentiate the third time. So that will be delta YL equal to AI minus YT. And so what they are actually trying to capture is just subtracting that predicted output from the actual output to now get the error that you have at each point. So the calculus you used to know is just this whole gradient descent idea, where you have to move from the top of that mountain or something to the descending from that top of the mountain to the lower part of the mountain. So when doing that, you have to always look out for the shortest path that it will come to do that. So there is, in the case of regression, where the error that we are looking at is the mean square error, or MSE. While in the case of classification, we are going to be looking at the cross entropy loss. So the cross entropy loss is just minus summation of yi log of y cap. So it's still the same kind of approach that we're using for the regression, but in the case of classification, of course, we are now dealing with labels or some stuff or images of a cat or a dog or something. So definitely we just have to look at how precise we get them, or how we don't, the accuracy of what we did and all that. So it's always quite easy to figure out those things. However, deep learning, as interesting as it looks like, it also comes with challenges. And one of it is overfitting. Now, remember, because of the complexity of this whole network, you are likely going to have challenges where you could get stuck, during them. one of the challenge that we have is overfitting. When you do not have a lot of data set, you are likely going to have an overfitting because the deep neural network is data hungry. It needs a lot of data, a lot of data, a lot of data. So when you don't have much data set for it, it will begin to have issues about overfitting, where the learning rate from the training and that of the testing will be quite bigger, with each other. So that way you will actually know that something is wrong. And then there is the issue of the vanishing of the gradient descent or exploding descent, which I actually made a big emphasis on that. That when you are using the sigmoid function, one of the issues it has is the vanishing of the gradient descent. Now, the more complex it becomes, the more difficult it is for you to get to the local minimal. And because of that, to the global minimal, sorry, so you could easily get stuck in the local minimals. And if you're not careful, that could create a whole problem for you. So you have to optimize that. Now we also have need for large data, to compute. Like I said, part of the problem we have is data because it's data hungry and it's very complex. So that data to do that computation, it's always going to, and it will take time because it takes resource. So most of the time, when the layers become very deep, you know definitely that you cannot be able to handle it on your CPU. You are likely going to need a GPU to do that. We also have the regularization issues where you have to prioritize which of the nodes you have to drop out and which of them you have to keep. Although there are things like lasso and rich regression that could help us in being able to select the right ones to keep and the ones to minimize, but the L2 dropout regularization is one thing you have to take note of. And also another thing is the batch normalization, because I told you, you can't just use this put all the data. It will likely split it into batches, so it could learn via this feed forward and backward propagation that we highlighted. So that could actually take a lot of time, but again, it's quite interesting because it helps us to see the learning error for each learning rate for each of the batches. Now, on the data side, we have the issue around big data. So you need a lot of data to do that. But luckily for us, we are in the age where data is very, very much available. But imagine if you are looking at a specific task where you do not have lots of data, you cannot really be able to generalize easily without having data. Then there is the issue of the big compute. Like I said, you cannot be able to handle it in your PC. You have to employ the use of GPUs. So it's quite a challenge if you cannot lay your hands on cloud computing facilities or a GPU to help you. And then architecture search. Most of the time, you cannot be able to use one particular architecture. You have to prioritize the architecture that actually capture your problem. So sometimes, trying to search for the right architecture, which has to do with how many stack hidden layers do you have to put and all that. That could also be quite a challenge. Now, remember, the more you stack this layer, the more you are dealing with a black box problem. So imagine things like ChatGPT. Some of these things can have billions of networks, like billions of them. So how do you know what is happening in each of the nodes? It becomes very difficult for you to be able to know what's happening in each of the nodes. Just 2, 3, 4 nodes, it's even considered a black box, not to talk of when you have millions or billions of them. So the issue of interpretability is quite a challenge when you are dealing with the deep neural networks because they have impressive performance. Trust me, most of the time, some of the image challenge, if you use things like logistic regression or random forest, you will likely get a very low performance, probably if you try 60, 70%. But the moment you use a deep neural networks like convolutional neural network for that image start, you may even likely have a 99% or 96%. So it does very well. But the problem is, how does it arrive at this percent? Because the more you stack these layers, the more it become abstract to you, and you won't be able to know what is actually happening inside the layer. So you have to you make sure that you build the architecture in such a way that it could have some interpretability abilities, so you could understand how the algorithms are making decisions to arrive at, for example, a cat or a dog. Now, another advantage of it is that it is future engineering free. Most of the time, you don't have to, like the traditional machine learning, you have to be the one to tell it which features are important, what it should prioritize. No, in this case, you don't. You don't need to get those pictures of a cat and a dog and all that, throw it into it, and then it will be able to, prioritize what makes it think that this is a cat and what makes it think that this is a dog. But if you are using the traditional machine learning approaches, you have to specify most of these features for it to be able to do that. So that future engineering flexibility that it could do that on its own gives it a very higher advantage than the traditional machine learning approaches. It is also more accurate, like I said, because we stack so many layers, so it has a lot of time to regurgitate information within itself before it finally gives us an output. So that alone gives it an advantage, and makes it much accurate than the traditional machine learning rule-based systems that we have. It has faster models. Most of the models that we have, they are very smart and very fast in arriving at their decision, especially when you have the computing resource. It could be very, very fast, and you'll be wondering, wow, how could it have processed this information within just few minutes? So I think with that, I don't think yeah, I think we do have, yeah, so it's basically some of the things. So when we talk about the GPU, this is actually how the GPU looks like. This is how the GPU looks like. You can use it to train the machine. So when we are just talking of the GPUs, just know, then there are availabilities of packages such as the Keras and TensorFlow, which makes it easy for us to adopt some of these techniques, and also new models that have been put into it, and all that. So it is still the same materials where we talks about the propagation and all that, but I will send it for you guys for the reading materials for this class. So I think with this